Hi, and welcome again to my Physics Online video lecture series. Today's brief lecture, we're going to be talking about Gauss's law as applied to some extended objects. You've already encountered by the time of this video Gauss's law proper. Gauss's law from an algebra-based physics perspective and in general, what it says is that the total flux, total flux of an electric field, and we basically denote it as total through closed surface, is equal to the amount of charge enclosed, and that could be represented by a capital Q for an extended set of objects or a lowercase q for individual point objects, divided by this constant epsilon naught, where epsilon naught is what's called permittivity of free space, which has this value of 8.854 times 10 to the negative 12. The usual unit we use is farads per meter, but for those who don't yet know what a farad is, because we haven't covered it in class, that's 8.854 times 10 to the minus 12 coulombs squared per Newton meter squared. Okay, so that is Gauss's law, as long as you have a closed object. And a reminder that closed objects have to be basically three-dimensional surface. So important note, need to use 3D surface for Gaussian, or for Gauss's law. And of course it also has to be a closed three-dimensional surface. A hemisphere without the bottom is three-dimensional, but it's not closed. Okay, so what I want to do is apply Gauss's law to a few situations, and we'll try to obtain what the field is for a given charge distribution in these circumstances. The other thing that you need to recall is the rules for electric field lines. There's a new rule here, so recall electric field lines rules, but it's not even necessarily a new rule. It's just kind of a further explanation of an old rule, namely denser E field lines means stronger field. And what you may be thinking here is that, let's say I've drawn some element of charge somehow like this, and maybe my field lines end up looking somehow like this for this charged object. So maybe there's clusters of charges in some parts and less charges in others. And so you might say, well, field lines are very dense here, so I have a stronger field compared to, say, right here where they are relatively less dense. And that is kind of correct, except for that the right way to look at it is if these lines all represent lines that are in the XY plane, the plane of the screen, then this object is really kind of oriented along the Z something plane. So it's sticking out of the page and into the page. And so we're looking at how many field lines poke through the object. In other words, we're looking at the flux of the field lines. Now, the new thing, so this is a statement about flux, and that is kind of new in as much as we didn't know about flux when I first made this statement. But the other new thing that could be added to it is that if the diagram is correctly drawn, then, so a correctly drawn diagram, whoops, that's not how you spell correct, will have this feature, that number of field lines poking through a surface, passing through the surface, is proportional linearly to flux through a surface. Okay, and so this right here is kind of important for us. Now, we used that to figure out Gauss's law in the first place, essentially by arguing that if you have, let's say, an enclosing surface, maybe it's a sphere or a spheroid, and you have, say, a charge out here, such that your field lines look like this, that the net flux through the sphere is actually 0 because every line that enters also exits, and vice versa. So this is total flux equals 0. Now where I'm going with this is, let's now take a more complicated system. For example, maybe we have a long line of charge, like so. And maybe we have some positive charges on it, like so. And so our field line drawing for this long continuous line of charges would look something like the following. From the side view, you have what appears to be a set of stacked lines. Now remember that you're only getting the lines in this one plane. There's lines coming out towards you. There's lines going in towards me. So if we were to look at it from the top, you'd also have this. Now to use Gauss's law, what we have to do is pick an appropriate Gaussian surface. I'm going to draw my Gaussian surface in purple. And what I want is ideally a surface that is kind of symmetric. So for example, something that maybe has a shape like this when looked at from the side, and then maybe a shape like this when looked at from the top. So if this is the top view and this is the side view, then what I really have is a cylinder of some sort. Okay, so Gaussian surface, choose cylinder. Let's give it a radius of r. We'll use little r for our radius. And let's give it a height of h. Okay. Last but not least, we need to define for ourselves how the charges are distributed on this long line of charge. If it's infinitely long, then there's infinitely much charge, but there's a difference between an infinity in which the charges are stacked like this versus an infinity in which the charges are stacked more like this. Okay, so we could have more or less dense. And so that density is what we call lambda. So lambda will be defined as basically charge on line per unit length of the line. So if I take a length of L for this line, so from here to here is L worth of the line, then the amount of charge between these 2 points, Q total, Q on L, is L lambda. Okay, now that's important because it lets us basically set up Gauss's law. So let's work Gauss's law out. I guess I'll work it in black. So Gauss's law on the one hand says that the flux from the E field must be the enclosed Q divided by epsilon naught. And looking at my cylinder, all of the line within the cylinder is enclosed within the cylinder, but only a certain length of the line. So basically the entire thickness is enclosed, but only a certain portion of the length is enclosed. And so to get Q enclosed, I can use this linear density lambda, and I can multiply it by the height of the cylinder H. Okay. On the other hand, if I just do a flux calculation, where these are my E field lines, I can see that from the top and the bottom there's zero flux because the E field lines run parallel to the top of the cylinder and the bottom of the cylinder. But along the sides, my flux phi E, which is E dot A, becomes E at R. So you could call this like E of R or something like that, times the area of the sides. Well, the area of the sides is your lateral area, so that would be your circumference 2 pi r times your height h. And if I put these two equations together, E times A, or E of R times 2 pi r h, should be equal to lambda h over epsilon naught. So E of R times 2 pi hr is lambda h over epsilon naught. That means that E of R is equal to lambda h over 2 pi hr epsilon naught. And notice that the h's will cancel. And so finally what this means is that my total E field is a function of distance from the wire and is given by lambda divided by 2 pi epsilon naught r. And that gives me my field strength some distance r away from the wire in terms of this charge per unit length. Another scenario would be a plane of charge, so an infinite plane of charge. And as we had to do over here with the dense versus the sparsely arranged charges, so with the plane. So we define for ourselves sigma, and that'll be defined as charge per area. So essentially, like if I were to section off a piece of the plane and a particular area of the plane, how much charge would I have? Well, the answer is Q is equal to sigma times area. So writing it a little neater, you get something like this. Now again, I need to make a Gaussian surface. This time I choose a cube. Now there's only two faces of the cube which are going to have non-zero flux through them. I'll shade those two faces. Shaded faces have non-zero flux. In fact, they both have the same amount of flux. Again, if this is a cube with side length x, then the flux would look like E times x squared, or E of x times x squared. At the same time, that flux by Gauss's law is Q enclosed over epsilon naught, which is sigma x squared over epsilon naught. So if we combine these equations, we get that E of x is sigma over 2 epsilon naught, where the factor of 2 comes from there being two sides. And that's it.